Bismillah ar-Rahman ar-Rahim. I think so that is I will start because I think so today, as I said, we have finished and this is why I realized that many students did not attend today, and many of them they have also seen projects. Well, as I have mentioned today, we will try to cover the same aspects of things that could come in the final exam. And the reason why I'm doing this so that I can feel that you're comfortable for the parts that are related to the hazard study and what we have taken the last two chapters. So going and looking at some examples that I'm showing you here. So one of the examples that we will have is that we are going to give you one of the systems, and this is a system that you have here, and here I'm telling you what are the nodes, but you may have within the exam without these, okay, without the nodes, without telling you what are the things that you need to put an eye on for safety. And this is where we need to think about. Without it, I'm going to show it to you again now. Why I'm showing it to you, so that it just triggers some ideas in your mind. So what I'm going to say simply, I'm going to give you a figure like that, probably, or without these things, without the nodes here, what are the areas that you need to concentrate on? I'll keep it to you. And then I will ask you to run an what if analysis, or for example, write a hazard study. Now, these two tables are going to be given to you in the exam. Okay, so I'm going to tell you, please write a what if analysis, and then I'm going to give you this table just to be a guide for you. Or please perform a hazard study, and then I'm going to give you this table here. Now, talking about what if and the hazard study, they are very similar. They are very similar. Why? Because the what if somehow explains these three together. So what if the temperature in the reactor increases? Which means here you're going to write, if it was the details, temperature high or higher, where guide word and deviation means the same. Deviation means that it is higher in this case. Okay, and here you go, what if the temperature in the reactor increases? Let me zoom out. Okay, so you can see that what I have written here, what if, looks very similar to what I'm writing here, except that this is the hazard study and this is the what if analysis. And then you're going to write the consequences, which is the same. The safeguards is different from what we have here. Safeguards is exactly like recommendations, and what you want to do, but you will not state them as a recommendation. Here you will state them as a recommendation, but it's the same point. However, here in the hazard study, you need to put the causes, which is different. Which means causes means why did the temperature go higher in the reactor? Okay, why did the temperature in the reactor went higher? And in this case, when you say this cause, you put the reasons why the temperature went higher in the reactor, because now you're thinking about it. Cooling water. I'm explaining, but I need to explain this before so that it becomes better. And what do we have here? We have a system, and this is a reactor. The reactor is a CSTR, continuous stirred tank reactor. That means we have an input and we have an output. It's continuous. Stirred, we have a stirrer. This is a tank, and it's a closed vessel, as we can see here, and it's a reactor. We have written as a reactor. It's an exothermic reactor, which means that with the reaction, the temperature goes up. And while the temperature goes up, what we need to do? we need to cool down so that we bring the temperature back to the optimum temperature. Well, cooling down is to bring it back to the optimum temperature. However, if the cooling water here, for any reason, stopped, if this cooling water stopped, we will have a runaway temperature, and our temperature will start increasing. Now, temperature increasing here it's not safe. It's not safe maybe for the walls. I'm not sure how the walls are built so that they can withstand high temperature. Number two, if the temperature goes up, you will have the pressure going up as well. Why? Because you're going to have liquid and you're going to have gases. Oops. Let me show that to you. Okay, just a second. I don't know what happened, but many things happened. Okay, so what do we have here? So we are going to have, for example, the level here, and this level, which is inside, and while temperature is going up, I would expect this level to go down. While, because you will have a lot of this liquid sitting inside here will vaporize, and having more pressure, it will exert, and having more gases, it will exert pressure here on the walls. It's not pointing exactly, just because this is not a PDF, this is a Word, and this is why I cannot draw in it easily. And you will have a lot of pressure here, so that is an issue. If you have a cooling water blockage, or it's just stopped for some reason. Now, going back to the idea, so what we are going to do here, we are going to write what if analysis, or the hazard study. So what if the temperature in the reactor increases? Consequences, the pressure will increase, which could cause an overpressurized vessel, causing blow off, and a disaster, of course. So safeguards, what are the safeguards? Now, looking at our figure here, we already can see that there's a temperature controller. So there is a temperature controller which prevents the temperature to run away. So the temperature controller says that what? If the temperature inside the reactor changes, whether positively or negatively, and if it was, for example, 25 degrees, and that is your temperature, the set point. If it went to 27 or 28 or 20 to 18 and whatever, the temperature controller, the switch is going to put on the temperature controller, and the temperature controller is going to take an action on this cooling water. Okay, the flow rate of cooling water. I'm going to mention some details now. Now, what is the reason why the temperature went out? Of course, safeguards. If you're going to put safeguards, you're going to say, I'm going to put a temperature. There's already a temperature controller, right? If there was no temperature controller, you're going to say temperature controller must be added. If you are really worried and there's a temperature controller, but you want to make it more reliable and more safe, you're going to say an additional temperature controller must be added. And the word additional here, if you can remember, the word redundant. Okay, so if you want to write additional or a redundant temperature controller must be added. Now you can see, like, I'm just writing what are the safeguards. If you are going to put a recommendation for that, you're going to just mention the same thing, add a redundant temperature controller. Now, the recommendations could take all the safeguards ideas, because you may have 3 safeguard ideas, but the recommendations, you're going to take one of them only. Okay, so the recommendations is not always a repetition of what's written in the safeguards. It could be only a selection to the most important point that you can see that you want to take on the using that safeguard. Okay, now going to the hazard study. If I'm writing the same thing, the consequences, what are the consequences? The consequences, I'm going to write this. Okay, so I'm putting the consequences. The causes, what are the causes? Now going back, the same figure, what are the causes? The causes could be, it could be because the temperature controller, let me go before that. It could be that the switch is not working. Okay, now because I said the switch is not working, I already have an idea in my head. That means I may have another switch also in parallel, which means a redundant switch. Okay, you see how my mind is thinking. So the switch is not working. Number 2, it could be the temperature controller is not working. Number 3, it could be the stem in the valve is not working, because here we have electrical signal to pneumatic signal, and you always say that we have pneumatic on valves, it's safer. It operates in what? That it operates that if you have electrical signal from 3 to 15 psi, it is converted to 4 to 20 milliamperes, so that it pushes the stem to close. When I say the stem, I'm not sure if you know that or not, but you already have taken this, Yani. So if you have a flow, this is a stem, right? Now I'm talking about a gate valve. Okay, so this is why I just put one straight line here, and if it goes down, it just blocks, and then it's like a gate, it goes up. Okay, so here it's because of the air pressure that pushes the spring. This goes down and closes this pipe here. Now, talking about putting on a pressure, pneumatic, and it closes. So if there's any problem with the spring, with the stem, with any problem with this, with any of these components or elements, you're going to have a problem that this will not close as required. It could be that that if this valve is fail close. I don't know if you know the word fail close. If fail close, that means if the valve fails for any reason, I'm talking about the example that it fails, that the stem is not working well, it fails. Now, if it fails, what happens? Does it close or does it open? That means it does not get the signal. It has no signal. Does it close or does it open? It depends on how we built this valve. We can build this valve that if you apply pressure, it closes, or if you apply pressure, it opens. Okay, so we built the valve to be, when they say air to close, that means I'm putting air, pushing air, so that it closes the valve, or air to open. When I mention air to close, I'm pumping air to close the valve. So if it fails, it will open. I'm pushing air to close it. If I don't have air, because I have no signal, it opens. Okay, so this is the case that what I'm talking about air to open. I'm pushing air to open it, and when it fails, it closes. طبعا, it will always be fail open. Why? Because if it fails, you want to cool down the reactor. but maybe I'm telling you in an earlier stage where you are required to develop a safety precaution and safety design for this process here. So what you're going to do, you're going to build it as fail open. If it fails, it will pump in cooling water to cool up the system. So talking about the causes here, you can see how many causes we have mentioned. And we have mentioned many causes. Something related to the switch. Now I'm not writing the details because I'm just making out of to make use of the time. So it could be related to the switch. It's related to the temperature controller. It could be related to the valve itself, where it is not built to be fail open. The valve is the cause is the valve is fail open. It could be blockage in the valve. I'm not sure how this is a good point or not, because if we know that we are dealing with sewage, something that's very viscous, we can't talk about that. But if we don't have information about that, I think my point is not very relevant. Now, depending on each one of these, okay, depending on each one of these points that I have mentioned here, if it was related to the switch, of course, I need to write more details about that. I mean, more details, that means the switch failed or is not working. So here's my suggested is to have a redundant switch. My suggested control access. Okay, use a redundant switch. Temperature controller failed. I don't know if you want to put another temperature controller. The valve is fail open. The valve should be designed to be fail close. The blockage in the valve, I'm not sure what to say about it, but it needs to be cleaned. If I know that there is a blockage in the valve, and there you can see that there is an analysis part where you need to understand this process. So if I don't give information about this, so I don't think so my last point should be written because it's not valid. But other points will always be valid for any operation, for any system. Now you can see how many points we just have mentioned here, just many points, and that is for the temperature of the reactor. And then I'm going to write something about the pressure, and I could write more, of course. And here the nodes just gives you an idea. The feed line could go, there could be a problem with the feed line. There could be a problem with the agitator. The agitator is not working. So the temperature increases at a certain point because it's not equally distributed. And that causes, again, the pressure will be, more gases and pressure will be high. It could be that vessel is not well designed to withstand high temperatures or high pressures. Cooling water line, there's a problem with the cooling water line. There's a problem with the output line, it got blocked. Now, all of the examples that I have given was only a small example about the temperature going up here. But when you know these nodes, when you know these points, the points, that means every line, stirrer line, cooling water, every line that we have for temperature control or for the cooling water or the input, the output, the stirrer, when you put these nodes in your head, you can put more and more points here. It just gives you more points. In the exam, I'm going to tell you, please identify, for example, 5 different cases, for 5 different what ifs in this case. Okay, so this is an example of the first part. Do you have a question in the first part? It's just an example of what could be coming in the exam, for hazard study or what if.
دكتور بس عندي سؤال.
ايه تفضل.
الحين يصير نقول مثلا what if the temperature controller fails؟
ايه يصير؟
تمام.
ايه يصير؟ What if temperature control fails? The consequences, the temperature will run away in the reactor, causing higher pressure because the cooling water طبعا ما قاعد يسعي. Safeguards، شنو تسوي في safeguards؟ تتكلم عن another temperature controller، 2 temperature sensors، ما أعرف، أي شيء في خاطرك. عادة another temperature controller is good enough. هذه اسهل جواب. اوكي صح. اوكي طبعا هني the property the HAZOP study you mentioned some more details as I've mentioned. What if the temperature goes higher, where the temperature goes off? You use the guide words which means something similar to that. You already have some guide words that I have presented. The guide words خلينا نرويكم إياها. It's always better to see everything. من هالguide words are they? Okay, that is a group of guide words where you have here flow more or level higher, مثلا temperature higher, lower, freezing, يعني vacuum. You can use even new words other than this word if it just helps you. But these are the very popular words. You have a problem with instrumentation. You see here, you have a problem with the temperature controller, or any temperature control is not working. You can write here not working, for example. So yes, these are the kind of things. And so these are like another example of guide words. I think so. I had a place where I mentioned here, yes, known, not none, more, higher, greater, less, lower, as well as, part of, reverse. So these are many ideas of guide words that also could help you within the HAZOP. Guide words for using to use for the HAZOP procedure. Great. Any questions? Okay, so that is one of the questions in the exam. Okay, I'm telling you, definitely you will get a question in the exam. What if HAZOP? However, of course, I'll not bring you the same figure. I'm going to bring you another figure. Okay, so definitely you're going to have something. Now, this table you're going to be using, if, for example, this is an example here. And what I'm going to do here, as I said that I'm going to give you a system. طبعا يعني شو نشرحها. Yeah, I think so. I'll say that. Now to write a fault tree or an event tree, we already told you that we will not let you draw the fault tree because that needs more time. And I'm thinking for the next time, maybe I put more effort for students to have less part of little quality, and I add more part of fault tree analysis. For you, you're not going to draw the fault tree. So I'm going to give you the fault tree. I'm going to give it to you. Hello? And now, giving it to you, you need to know some details. You can see here, it's written, the details are written here for the problem, where it's written here, the pressure switch failure, the pressure indicator light failure. On this example, that it doesn't have a pressure. And if I would have written a fault tree for this, I would have a temperature indicator, temperature light sensor, switch, and we know that it's a thermocouple sensor. What else do I have? And these are the main things. We don't have a lot of stuff here. Of course, I'm going to bring another example for that. But I'm just telling you that, for example, I give you a system, and within the system, I give you the fault tree. Now, giving you the fault tree, you are going to find these numbers. Okay, so you're going to identify these numbers. So my question will be, what is the reliability of this system to prevent the overpressure of reactor? To prevent the overpressure of reactor, what is the reliability of the system? Which means, what is the probability of the system that it will fail where I'm going to have an overpressure? So you're simply saying how many times in the year I'm going to have an overpressure in the reactor. Okay, how many times? And I'm going to give you the fault tree. And in future, inshallah, you will draw this by yourself. It's not difficult, wallah. But we didn't have enough time to train you enough for this. So I feel that's not fair to give you an exam or to draw it. Now in the exam you already have it. What you're going to do, you're going to work on it. Of course you will not have these numbers. Not have these numbers يعني شنو؟ خلنا محي brush. أظن هذه هو المحاية. لا هاي مو المحاية. Sorry I forgot يعني because I don't use this يعني محاية هكو. Okay. So what do we have here? Now we already have 0.13 and 0.87. You're going to have a problem without this and without the rest, of course. Hello. So when I ask about the overall reliability of the system, you need to know what is the overall reliability of the system. Now, where to get this information? The pressure switch failure, the pressure indicator light failure. So let's see here. Do we have something here we can use in the table? So I already brought the table. I'm going to give you the table in the exam. We can see here the pressure switch 0.14. The faults per year, pressure switch 0.14 faults per year. I'm going to bring everything back. Okay, pressure switch. Number of faults per year. واحدة واحدة. I'm going to do it one by one. So where's the pressure switch? High pressure switch. Pressure switch faults per year. That means this is mu. Mu is equal to 0.14. The reliability is equal to exponential to the power minus 0.14, which is equal to, just to get my calculator. Okay, so exponential to the power minus 0.14 is 0.87. 0.869, so it's 0.87. Now, if R is 0.87, P is 1 minus 0.87, which is equal to 0.13. Now, going back, this was what it is written here. Reliability is equal to 0.87, and the probability is 0.13. Very similar going to the pressure indicator light failure. Indicator lamp 0.044. Which means if I take the exponential of minus 0.044, exponential minus 0.044, that will be 0.957, because I'm taking only two significant figures here, so I'll say 0.96. And that is the reliability, of course, and the probability will be 0.04. Going back, 0.96, 0.04. Hello? Now, going up here, and this is tricky, but I'm not going to give you this in the exam. This is something more complicated because, but don't worry about it. And there's nothing complicated. It's always easy. Now, if we have an OR gate between two events that could happen, this OR, we already gave you the equations of for, OR, and AND. Going back to what we have taken. لا مو بدي chapter. If we're going back to this chapter, we already said that where you have OR gate, this is what you do. If you have an OR if your reliabilities, you multiply them. For me, as I told you, this is the way of how I memorize it, how to memorize it. So what do? I say the reliability. If I have an OR gate, I calculate the reliabilities, I multiply the reliabilities, and then I get the probability. And if I have an AND gate, I multiply the probabilities, and then I get the reliability. It's easier for me. If you want to do this, you still can do this. You can do this equation. You will get the same answer. So going back, so where we were, okay. So this is an OR gate. An OR gate, I think so. We said that we multiply. If you have OR gate, you multiply the reliabilities. So multiply the reliabilities, which means 0.96 times 0.87, you will have 0.8352. Okay, so the probability is 0.8352. The reliability is, okay, I'm going to octave. how to write this. Okay, the بعد ما اقدر اكتب. Okay. شلون اكتب. Okay, the probability is because this is not in whiteboard. I wish I took it there. 0.8352. So in this case, it's 0.84, for example, and then you have the reliability to be. Is this correct? No, the reliability is 0.84. So the reliability is 0.84, and then the probability is going to be 0.16. Okay, so it will be something like that. And then you continue on. Let me show you the way. I'm not going to give you this, so that I don't want to confuse you, because you get confused getting something like this here. So I don't want to confuse you with something new. Most probably you will get something that is straightforward like that. So in this case, here I have failure of a solenoid valve pressure switch. Again, you can see the pressure switch here is 0.13 and 0.87, very similar. And failure of solenoid valve, you can see the probability of failure of solenoid valve is very high. And let's go and see if we have solenoid valve here. Yes, solenoid valve is 0.42. 0.42 exponential to the power minus 0.42. It will be 0.66. 0.66. Okay, so going back 0.66, then the probability is 0.334. I think so you already got the idea. And then of course we have an OR gate. You multiply the reliabilities, 0.66 multiplied by 0.87, it will be 0.5, again 0.87, because I got a different answer. 0.87 multiplied by 0.66 is 0.574. There's an error here. This is where if you get things online and you get things wrong. Here's 0.474. If you find that I did a mistake, please tell me, but I cannot see that I did a mistake because it's an OR gate. Maybe he thought that it was an AND gate. Maybe he thought it was an AND gate. So if he thought that this was an AND gate by mistake, it's 0.34 times 0.13. The answer is 0.044. Still is not correct. Still is not correct. So I think so. There's definitely there's a mistake here. So it should be 0.74. And then you find the probabilities, which probability is 1 minus 0.74. The answer is going to be 0.426. And you start, of course, calculating from both sides. You get a number here, you get a number from the other side, till you get the final event here. And the final event, you're going to, of course, take what is here and what is there to get the final number here. And then you'll get how many failures per year, how many times. So when I ask you, what is the reliability? You already here found the reliability, but when I ask you how many times it fails per year, when you get your final answer, you already know that reliability is equal to exponential to the power minus mu t, right? And so now the only thing here that you need to find is mu. Okay, the only thing that you need to find here is mu, and of course we are talking about 1 year, so that is one. So you take the ln of both sides and find mu. So simple as that. So this is another way of how to find out. It's not another way. This is another question that you may get in the exam. What else do I have? What else do I have? I have one thing in addition. وين أحصل عاد? Okay, just a second.